Hi guys, in today's video we're going to be looking at the conservation of momentum. So this is sort of a law that's in line with the conservation of energy that we learned in some of the previous videos here. And so we will sort of see how to apply that today. So our first step is to recall the form of momentum. So if we imagine some particle A with some arbitrary velocity pointing in some direction, the momentum of that particle is just going to be its mass times its velocity. So first thing to recall is that this is a vector quantity, so we need to be careful that this has a direction as well as a magnitude. And so let's say maybe we have a second particle here, which is going with some other velocity, VB. So then the momentum of particle B similarly will be mass B times the velocity of B. And so we could do this for any number of particles. And whenever we're dealing with the conservation of momentum, the conserved quantity is going to be the momentum of all of these particles added together. So that's to say our conserved quantity is the total momentum, which is equal to momentum of particle A plus momentum of particle B plus ... So this is for however many particles you're looking at. And this here is what is conserved. This is constant at all times. So if we start out with a scenario, we add up all of their momenta, that should be the total momentum at all times, right? PA and PB individually could change, but the total sum has to stay the same. And so just like our conservation of energy, mechanical energy, was only true when we had conservative forces working, this is only going to be true when we have no external forces acting on our system. So for these momentum conservation problems, we have to be very careful to define our system very precisely and sort of pay attention to internal versus external forces. So in this case, what we could do is sort of draw a dotted line around our system and say maybe here we're only going to be concerned with particle A and particle B, so that comprises our system. So then we have to say our momentum of particle A and particle B, this total momentum, is conserved insofar as we don't have some external actor acting on these two particles, and therefore we can have internal forces. So particle A might collide with particle B, we might have those kinds of interactions, but as long as it's only particle A and particle B doing these collisions, we are okay, and our momentum, our total momentum, is still conserved. But when it's not conserved is if, say, we're standing outside of the system and we grab one of the particles and take it away, right? That will now cause a change in momentum because we have some external force acting on the system. So it's going to be very careful. You have to be very careful to sort of split up your system and be very sure of what the system you're looking at is. So this comes in handy in something like collisions. So you have a lot of collisions problems that are going to come up here. And so the basic form of those is sort of the same, and we'll see one today, where we maybe have a car A with a velocity moving to the right, and a car B with some velocity moving to the left. And so if we wanted to look at this through the lens of Newtonian mechanics, for instance, we would have a very tricky time, which is to say as soon as cars A and B collide, their hoods are going to crumple. There are going to be a lot of sort of these internal forces from each car on each other, and we just don't know the form of those forces. But one thing that we can say from our momentum conservation is that as long as we're only concerned with car A and car B as our system, the total momentum of A and B, which we see is pretty straightforward, it's just MAVA times MBVB, that total momentum is conserved even regardless of all of the crumpling and all of the little internal forces going on here, because we're not worried about any external forces on this system at the moment. So this is going to be a very powerful way to utilize conservation of momentum, and we see we can sort of utilize it to gain some insight without actually worrying about every little force that acts. So let's see how we're going to utilize this today. So the problem statement reads as follows. A 15 kilogram block is attached to a very light horizontal spring of force constant 500 newtons per meters and is resting on a frictionless horizontal table. Suddenly it is struck by a 3 kilogram stone traveling horizontally at 8 meters per second to the right, whereupon the stone rebounds at 2 meters per second horizontally to the left. Find the maximum distance that the block will compress the spring after the collision. At this point, you should pause the video, reread this problem a couple times, and maybe even try it on your own. Okay, so we have our initial scenario drawn out over here. And so for this problem, we're going to split this up into really two phases of motion. So we're first going to look at this collision, which will be the instant before and the instant after that collision. And then we're going to look at the case where this block is actually doing the compressing of the spring. So the reason we want to do that is if we look at our system here as our stone and our block, this is going to be the system with the colliding objects, and therefore the momentum of that system is going to be conserved in that collision. But just after that collision occurs, this spring is going to start applying some force to the block. So that's to say this spring will be applying a force to our system, and that will be an external force. And therefore, as soon as the spring starts acting, we don't have conservation of momentum anymore. So what we can do is think sort of conceptually in our heads of this collision occurring sort of just one instant before and then one instant after that collision, and everything still is okay there. We're saying the spring hasn't quite acted yet, and that will give us the velocity that this block right here gains from the collision, and then that basically gives us an energy term which we'll utilize to solve for this spring potential. So that's sort of the game plan here, but again, we want to start by just looking at this collision. And we said for the collision, because there's no external forces acting until afterwards, we do indeed have that the total momentum is constant. So that's to say our momentum is conserved in this collision. And in this collision, we have our initial momentum. This is our initial total momentum, of course. The initial total momentum is just equal to ms times v of the stone initial, and I'm going to say that to the right is positive. So in this case we see that these velocity vectors are vectors, so they have a direction. So we do have to keep track of positive and minus signs. In this case though, our velocity initial is pointing to the right, which I've defined as positive. So our initial momentum is just going to be mass of stone times velocity of stone. Of course we would normally have to add on the mass of the block times the velocity of the block, but in this case it's 0 because our block starts at rest. So this is our initial momentum, and then we can write down the form of our final momentum as well. And that should be, we can look at this scenario, that should just be equal to minus mass of the stone, velocity of the stone final, plus mass of the block, velocity of the block. And so again, the reason is the velocity of the stone final is to the left, which is negative. The velocity of the block is positive. So this here is our final momentum. Again, be careful to note this is only just one instant after the collision has occurred before our spring starts to act. So at this point in time, we can say that our momentum initial should be equal to our momentum final. That's just what it means for the total momentum to be conserved. So we can set these two equal to each other. And these are all quantities that we know except for the velocity of the block. So this actually allows us to solve directly for that velocity of the block. And we can get this as positive 2.00 meters per second. And so this is to the right, which is good because, of course, we see here, it looks like it should be to the right. And so if we solve through, we get 2 meters per second. So this is to say our collision gives this block a velocity initial of 2 meters per second. That's what it's going to start at. And now we sort of jump into our second phase of motion, which will be the point where this block here has that velocity of the block from the collision, but it's attached to a spring, so that velocity will really just be used to compress this spring by some amount. And that amount here will be our delta x. And so for this scenario, we see that instead of trying to use momentum conservation, which we don't have because the spring is an external force, we can use our conservation of mechanical energy because our spring force is a conservative force. So we can say that our initial energy should still be equal to our final energy. We're only dealing with conservative forces. So in this case, our initial energy is pretty straightforward. It's just going to be 1/2 mass of the block times v block squared. Right? We're not going to be worried about the stone anymore because that is not part of our system. At this point in time, we are just concerned with the block. I won't draw it, but this is really the only thing we're worried about. So our initial energy for the block is going to be 1/2 mass block v block squared, and that is going to be transferred entirely to spring potential, which is to say all of this energy goes into compressing our spring. And our spring potential is of this form. So we have a relationship here between this velocity we just solved for and the delta x, which is what we're looking for in the end. So at this point, we can just plug in our known quantities and then solve this energy conservation equation. And you should get that this is equal to 0.346 meters, which is to say that our spring is compressed by a distance of 0.346 meters from this collision. Okay, so let's review what we've just done. We broke up our problem into two different phases of motion. So we first looked at the collision of the stone and the block and used the conservation of momentum to solve for the velocity of the block just after the collision. Then we looked at the remaining motion, which was the block with its kinetic energy from the collision compressing the spring. So to find this compression, we just used the conservation of energy and solved directly for the delta x. Okay, so I hope this video was helpful, and I hope it sort of gives you an idea of how to utilize these various conservation laws to solve what could seem as very complicated physical scenarios. So if you have any comments on this video or any of the videos here, please post those on the link to the right of the video link on TED. Thanks for watching.